from the Chinese University of Hong Kong. Dr. Choi is an expert in geometric modeling, optimization, and scientific computing. His research spans surface and volumetric mappings, differential geometry, and their applications in medical imaging, data visualization, and computational mechanism. He has published widely journals such as Journal on Scientific Computing and Computer-Aided Geometric Design. In today's talk, Dr. Choi will introduce the concept of density-equalizing maps, a powerful framework inspired by density diffusion. He will show how this mapping can create shape deformations with controllable area change and demonstrate applications in shape registration, remeshing, and more. Let's welcome.
Thank you. Thank you very much for the nice introduction. My name is Choi, and I am an assistant professor in the Chinese University of Hong Kong. So first of all, I'm very happy to be here today to join the International Congress of Basic Science, and it's a great pleasure to be here seeing you all. And today I will talk about density equalizing map with applications. So we know that in many different science and engineering problems, there are a lot of issues about geometry and computing. For example, in biology, from time to time, we may want to study different kind of shapes, starting from the very simple 2D shapes such as insect wings to some more complicated shapes such as some 3D skull scans. So in these biological problems, we may want to study how these shapes are different from each other, or whether there are any kind of fundamental changes in terms of the geometry of them, and that requires a lot of studies of geometry and computing. And then in medicine, there are also a lot of problems which are related to geometry and computing. For example, if we want to study some kind of diseases, let's say some kind of brain diseases or some kind of blood vessel diseases, then from time to time we may want to also study their shape changes, and that would also require some geometric methods and also some computing methods to analyze these very complicated shapes with different complicated geometry and topologies. And also in engineering, we can see that there are a lot of applications that also requires geometry and computing. Let's say if we want to do some modeling on some engineering structures or study some kind of engineering materials. So in that case, then we may also need to use some geometry and computing methods. And finally, in computer graphics, if we want to achieve different kind of very amazing animation effects, or if we want to achieve different kind of visualizations, then we may also need to use a lot of geometry and computing techniques in order to achieve that. And we can see that for many geometry and computing problems, there are actually some key tasks that we want to achieve. For example, one key task would be registration. Registration means that we want to find a one-to-one correspondence between two shapes. And from time to time, we may also have different kind of requirements between these shapes, such as some kind of correspondence between features. In this case, we have some correspondence between the nose or the eyes and so on. So how we can find a good mapping from one shape like this to another shape like this would be the registration problem. And then another problem would be a shape analysis. As we just talked about previously, in many biological or medical problems, we want to analyze some kind of shape changes in terms of these kind of organs or these kind of structures, so that we can detect their shape anomaly and also use that as a criteria to identify some kind of diseases. So in that case, we may also need to do some kind of shape analysis based on some geometric information, such as curvature or some kind of distortions. And then texture mapping would also be one key task in geometry and computing. If we want to design some kind of fancy textures on a surface, then we may from time to time also need to use different methods to achieve that. And different mapping methods, different geometric methods would also affect the effects of this kind of texture mapping. And then if we want to achieve some kind of continuous deformations, some kind of shape deformations, then that would also be one very important task in geometry and computing. And finally, remeshing is also a very practical application in geometry and computing. If we want to design or if we want to improve the mesh quality of a complicated shape, then we may also need to come up with some methods in order to achieve that. So we can see that in geometry computing, there are actually a lot of tasks: registration, shape analysis, texture mapping, shape deformations, remeshings. And one common task that would be involved in many of these approaches would be something called the surface parametrization. So what is surface parametrization? Surface parametrization is basically the process of mapping a complicated surface to a simple domain. For example, if we have a genus zero closed surface, which is a topological sphere, then in that case, we may want to map it to just like unit sphere, which is kind of like the most natural choice. And then if we have some simply connected open surface, that means we have a surface like this with one single boundary, then we may want to map it to some other planar domain. In that case, there are actually many different choices. We can have like squares, we can have unit disk, or we can have some more arbitrary domains, which are planar domains. So as long as they are topologically equivalent to this simply connected open surface, then that may be one suitable choice for some applications. And then what if we have some more complicated surfaces, such as these ones, which are like surfaces with holes? So there are some kind of like holes or like boundaries, multiple boundaries. So in this kind of like multiple connected open surfaces, then one natural choice would be to map it to a planar domain with holes. Then in that case, we can still do some systematic comparison between them by using these kind of like standardized domains. But then we will also have to consider how we can handle these different holes like in a systematic way and also in a low distortion way. So there are many different methods that we can use for surface parametrization. And like if we use different approaches, then they may have different effects. So for example, if we use conformal mappings, which is a very common method for surface parametrization, then a good thing about them is that like they will preserve angle. That means they will preserve the local geometry, but they may not preserve area in the sense that the area distortion may be very large. So this is one example. Here we have a lion vase model, and if we use a conformal parametrization, then it will be mapped to a very like a shape like this. And you can see that the lion head is actually mapped to a very small region. So, but if you just look into these kind of like other features, then they are actually like pretty well preserved in terms of their like shape, in terms of their angles. So that's a feature of conformal parametrization, angle preserving parametrization. And as you can see here, like the area distortion of some parts may be very large. While if we use an area preserving mappings, then the good thing is that it will preserve area but not angle. So here is one example showing like typical area preserving parametrization of this lion vase model. So in this case, we can see that the entire like head region of this lion vase model will be mapped to a pretty large region here in this planar domain. And that is kind of like indicating that it's actually pretty area preserving. But as you can also see, like towards the boundary of this like model, so all these like circular features will be kind of like squeezed and distorted quite a lot, and that means they are actually not angle preserving. So there is like some kind of like trade-off between this kind of like angle preserving or area preserving mappings. And so more recently, there has also been some considerations of like some more flexible like choices. For example, one choice would be the quasi-conformal mapping, which is kind of a generalization of conformal maps, which allows us to have some kind of distortion in terms of the angles, but then we still want to control it and have it bounded. So that's basically quasi-conformal mappings, a generalization of conformal maps. And then, as we also like just talked about previously about registrations and so on. So from time to time, we may also have some other criteria that we want to achieve, such as we want to have like balanced distortions or like landmark matching properties and so on. So let's say if we want to have like two human faces mapped to two planar domains and then do some comparison between them, then we may want to have like the eyes and the nose mapped to consistent regions, so that when we want to like find a correspondence between them, that would be much easier. So here we can see that like there are many different choices in terms of like the mappings and also the criteria, whether we want to have more like angle preserving mappings or area preserving mappings, whether we want to preserve some kind of like landmark features and so on. So there has been a lot of algorithms that have been developed for like both conformal mappings and also area preserving mappings. So I would say that for conformal mapping, there are like far more than for area preserving. Area preserving is kind of relatively like new in the sense that maybe like over the past like 10, 15 years, there are quite some like methods which have been developed. But then for conformal mapping, it is like over like 2 decades or more. So we can see that for many of these different like basically mapping problems, one common feature is that we actually want to achieve some kind of shape deformations. We want to be able to deform one shape in order to like get another like shape, and then we want to find some way to control the shape changes in some way so that like it gives us some kind of like desirable effects. So talking about shape deformations, there is actually one seemingly not very relevant like approach, but it's actually like in another area, which is in the like cartography. So in cartography, there was actually one approach called the diffusion-based cartogram in 2004, and so in cartography, people like to like use some kind of like deformations, also shape deformations, but not achieving these kind of like medical like imaging effects or some kind of like computer graphics effects. They would like to just distort some kind of geographical maps based on some kind of prescribed information in order to achieve different effects, mostly for visualizations. So in 2004, Michael Gassner and Mark Newman developed one method for this kind of diffusion-based cartogram to achieve like a new way to visualize data. So their approach is as follows. They try to compute some kind of mappings that achieve shape deformations guided by density diffusion, and where this kind of density diffusion is based on some prescribed informations, which can be populations defined in like in different regions or countries, or like the gross national income, or if you like coffee, then you can also even use coffee consumption as a criteria to do a cartogram. So here we can see that this is the ordinary like world map, and then if we use this kind of like diffusion-based cartogram approach to compute a deformation of this like geographical map to like the target effects, then you will see that for the population cartogram, you will see that different countries are expanding or shrinking based on the actual like population, and also for the like gross national income or for the coffee consumption. So we can see that here. Of course, this problem is not exactly the same as our surface quantization problems or like the geometry and computing problems that we just talked about previously. But the idea is quite similar in the sense that we would also like to find some way to distort a map, to distort a domain, so that we can achieve some prescribed effects. So in a few years ago, we tried to like extend this approach to the problem of like surface quantization and surface mapping. And we find that basically the key idea of this density equalizing map is actually just that we are given some domain. It can be like a planar domain, it can be a 3D domain, it can be some other surface domain. But for simplicity, we just start with like a planar domain. And then we are given some kind of like prescribed density. We have some high density region, we have some low density region. And then what we have to do is just that we can solve the diffusion equation, and then from the diffusion equation, we can get the velocity field. And from that velocity field, we can compute the displacements and use that displacement to guide like how different parts of the domain should be like deforming. And then at the end, when the density is equalized, you will be getting something like this. And that's basically the key idea of density equalizing map. So of course, for the case of geographical maps, planar geographical maps, we can achieve this pretty easily. But what if we want to handle surfaces or like some more complicated domains that we just introduced at the beginning, like different kind of surface with different topologies, or like if we want to achieve more different effects and so on, if we want to achieve either maybe conformal or area preserving or some balance distortion mappings, how can we achieve that? So a few years ago, we developed one work for surface density equalizing map, which is basically for surface parameterization. And the basically idea is that like we want to develop a surface parameterization technique based on this density equalizing map principle. And in this work, we first focus on simply connected open surface, which is just topologically equivalent to like a unit disk or a unit square and so on. So that gives us some like easy way to extend this like previous idea of density equalizing map to this kind of like surface mapping problems. So by running this or by using this approach, we want to achieve the following. We want to be able to enlarge or shrink different regions in order to achieve different surface mapping effects. And also, we also want to try to achieve the area preserving mapping, which is one of the major like mapping methods that we just introduced previously. So the approach is as follows. So we start with some given surface, and then in the next step, we will be computing some initial flattening map, and then we will be developing some mapping methods for computing these kind of like density equalizing map on triangular meshes. And then with that, then we can easily control the mapping criteria. We can easily control the mapping effects to achieve like different like final results. So I will be introducing like these different approaches. I mean these different steps like one by one. So first of all, we want to achieve like an initial flattening map. That means we want to be like we are given one simply connected open surface. And then we first want to find some way to flatten that onto the plane. And of course, there are many ways for us to flatten that onto the plane. But here, what we adopt is one approach that is we first handle the boundary of that shape, and then we try to handle the interior of that shape. So for the boundary, we can extract the surface boundary just by considering these kind of boundary vertices, and then we can compute the curvature of that boundary curve, and we can use a curvature-based method to flatten that onto the plane. Basically, we can reconstruct a planar shape, a planar curve that is with the same curvature information as the 3D curves. But of course, there may be some kind of discrepancy between the endpoints and so on. And so we can actually just use a very simple a correction step to kind of connect the endpoints so that it will give us a smooth shape. And that would be serving as the initial boundary of this initial map. And once we have the initial boundary, we can then consider how we can handle the interior. And for the initial map, we can just use a very simple method. We can just use the tip embedding method. And for the tip embedding method, we will just need to compute the graph Laplacian. And the graph Laplacian is given in this formula. So the weighting will be 1 if there's an edge between two vertices. It will be minus of the summation for the diagonals, and then it will be 0 otherwise. And by just solving this graph Laplacian equations based on this boundary that we obtained, then we can already obtain the initial tip embedding mapping. And that will be serving as the initial map for the subsequent computation. So one thing here is that in the original approach in this 2004 cartogram geographical mapping approach, so when Gassner and Newman try to compute this kind of density equalizing map on this kind of geographical maps, there's actually one issue. The issue is that, of course, we can define different quantities, such as the populations or incomes in different countries or regions. But then there is still the C. The C is something that we don't have any information on that. So it turns out that if we want to allow this entire shape to deform, then one key idea is that we can actually just define the quantity in the C as follows. We can just set the density to be the average density of the entire shape. So that means we can just consider all the populations in different countries, regions, and then the C will be with the average density. So the good thing about this is that we can then allow the entire domain to deform. So there will not be any constraint in terms of the shape deformations of these different countries, regions. But then it will also be able to allow us to avoid any infinite expansion. So even if we have very extreme density, or if we have a very extreme quantity that we prescribe, so it will just give us some kind of highly distorted map like this, but then there will not be any infinite expansion. So that's the good thing about this kind of a C, and it's actually necessary. So this kind of auxiliary region is necessary. And coming back to our approach, so we are handling surface mapping, surface parameterization. So we are only given the surface itself. We don't have any C outside. So if we want to further achieve these kind of shape deformations without any limitations in terms of how the overall shape is changing, then we also want to have a C. So in this case, what we do is that we can set up a C region, which is outside the region of interest. And the way that we set up this C is that we can just use a simple reflection. So suppose we have a domain like this, which is the region of interest. Then we can just put it into rescale it into the unit disk, and then we can just do a reflection. By doing a reflection, the good thing is that we can easily construct a C. So the blue region would be the C that we consider in our approach. And another good thing is that by the nature of the reflection, things outside or farther away from the center will be with causal triangulations. So in this case, we can see that those regions are actually not affecting the computations quite a lot, but then with some causal triangulations, we can kind of reduce the computational cost, making it more efficient. So that's the good thing about using this kind of reflection approach to construct the C. And once we have constructed C, we can then try to develop a method and iterative scheme to solve for this kind of density equalization on a triangulate surface or triangular domain. So first of all, we can just define the initial density rho to be population divided by the triangle area. So this is basically a discrete version of the density. And the population here is basically any quantity that we want to like prescribe. So in the case of like geographical maps, you can prescribe incomes, you can prescribe populations, and so on. And here we just call this kind of quantity called population. But you can set, for example, if you want a region to be like enlarged twice, then you can just set it as 2. If you want it to be like shrinking like to be half, you can just set it to be 1/2, something like that. So you can just set that kind of like population based on your desired effect. And then once we have set up this kind of initial density, then we can just solve the diffusion equations. And here we can just have a pretty simple discretization of the diffusion equations by using the triangle mesh. So on the triangle mesh, the cotangent Laplacian will be the discrete version of the Laplace Bertrami operator, and the cotangent Laplacian will be given by this formula where we have like 2 opposite angles alpha and beta, like opposite to the same common edge, and this will be like the formulation of the cotangent Laplacian, and also we have the area matrix AI. So the area matrix will be just 1/3 of the sum of the one ring neighborhood area of a vertex. And with this, then we can after we solve for the diffusion equations, we can then get the density gradients. And again, the density gradients can be discretized on like either the triangular face or the vertices. And once we have that, then we can use the density gradient to update the vertex positions. And then we can just repeat this procedure iteratively until the density is equalized. So that helps us achieve the desired density equalizing mapping effect. So here are some examples, some simple examples about like different kind of like mapping problems and also this density equalizing mapping effects. So we start with some simple problems. We just start with some 2D domains, which are triangulate domain. So in this case, here are the input surface. So for example, we can have a square domain with like 4 different different density regions. Basically, the ratio is just 1, 2, 3, 4. So this should be 1, and then 2, and 3, and 4. And then in the mapping effects, you will see that like the region with lower density will shrink. The region with higher density will be enlarged. This is the initial density, like basically that's just approximately 1, 2, 3, 4. And then the final density will be highly equalized. And you can also see that the density actually, like the density error actually decreases very rapidly. Like after a few iterations, it can already give us a highly density equalizing effect. And it can also be applied to other like domains. For example, you can have a hexagonal domain. And again, you can define like different density at different regions, like with different ratios like 1, 2, 3, 4. And then this is the final mapping result. And you can also see that the boundary itself is deforming freely. So it will not be limited to the, like just the same like hexagonal domain. You can have it being distorted like based on just the actual deformations. And again, for this example, you can see that the density error actually decreases very rapidly. So after showing some 2D mapping results, we can also show some 3D mapping results. So suppose we have some 3D surfaces, such as a surface like this, or a surface like a lion head surface. As we just mentioned, we can start with some initial map, which is just a way for us to start our iterative scheme. So the initial map would be something like this or something like this. So in both cases, you can see that like they are not yet deformed, but then like in the final mapping results, and here we are setting the density to be like based on the original like triangle area. So in that case, then the final mapping will be an area preserving mapping. So as we just mentioned previously, you can set different density at different regions. If you just set the density appropriately, so that like you just reflect the original triangle area ratio, then in the final mapping results you will be getting an area preserving mapping. And you can see that like for example in this case, originally the eyes and the nose are much smaller, but then in the final mapping results they can be kind of restored to a correct size. And here's another example. We have a more complicated shapes, and then we can just like flatten that onto the plane and then compute the mapping, and then we can easily achieve different deformations of like enlarging certain parts or shrinking certain parts. So that's some examples of surface density equalizing maps. And so in the previous examples, we have allowed the overall domain to kind of change in shape. But of course, in some cases, you may also want to kind of restrict the shape to be kind of like the overall shape to be unchanged. For example, you may want to have like originally just a unit square, and then finally you may also want to just have a unit square. You don't want it to be kind of deforming freely. So in that case, we can also enforce that in the density equalizing mapping computations. And this gives us the shape prescribed density equalizing map. And the way to achieve this is that we can just enforce a Neumann boundary condition when we compute the mapping, when we do the iterative process. And in this case, we may actually drop the C part because the C was set up to allow for free deformations. But here we want to have a kind of like a prescribed shape boundary. So in that case, we can just drop that C part and then just use the Neumann boundary condition. And all the other computations are just the same. So the effect is that you can see that the points can still slide along the boundary. So for example, here you can see that the red region is expanding. So the red points are actually, the boundary points here are actually going quite a bit up. And then the boundary points here are going quite a bit squeezed quite a bit here. So the points can slide along the boundary, but then they may not go outside, or they may not be going inside the shape. So that's how the shape prescribed DEM works. And so this is one example. And then here are some more examples. So this is just the example that we showed previously. And then this is another example showing that if we want, we may also set the prescribed shape to be in some other aspect ratio. For example, we can set it to be with height greater than the width, and then we can just run the density equalizing computation inside this domain. And again, we can achieve the prescribed effects. That is, that's the overall shape will not be changed, but then the points will be moved will be able to move freely inside this shape. And we can also have some kind of circular boundary constraint, or some kind of elliptical boundary constraints. And in this case, so we start with some kind of hexagonal domain, and then we try to map it to we want to enforce the mapping result to be a circular shape or an ellipse shape. So that's also possible. And then you can see that inside the ellipse shape or the circular shape, the points will be moving according to the prescribed effects. So some parts will be enlarging, some parts will be shrinking. And again, we can also do this for the actual 3D mappings. So we have an input surface in three dimensions, and then we can start with some kind of initial flattening map, and then we can compute the shape prescribed density equalizing mapping computations. And in the final results, we will be getting something like this if we want to achieve an area preserving mapping. Or we can also achieve an area preserving mapping that maps this kind of lion head to a square domain like this. And if you want, you may also want to set up some other prescribed effects. For example, you can have the eyes or nose enlarged in the mapping results. And here is another example showing that we can enlarge just the nose part like that. But then the overall shape is kind of prescribed. So this will be a rectangular shape. This will be a circular shape. So these are some possible outcomes that we can achieve using this kind of shape prescribed density equalizing mapping approach. So one application of this kind of density equalizing mapping would be surface remeshing. So at the beginning, we talked about surface remeshing as one common applications in geometry computing. And so if we apply this density equalizing mapping approach, we can actually achieve surface remeshing quite easily. So the approach is as follows. So we can first map this kind of given surface onto the planar domain using the density equalizing map. And then we can reconstruct a new triangulation on the planar domain, which is much easier than constructing that directly on the surface. And once we have constructed that on the planar domain, we can just use an inverse mapping to map it back to the original surface. So the good thing is that because of the density equalizing mapping, so we can easily control the remeshing effects. For example, if you want to have denser triangulation in certain parts, you can just when you compute the density equalizing map from here to here, you can just set the expansion of that part to be larger. So let's say you want to have more triangles in the nose region, then you can just apply a density equalizing map with the nose expand. So in that case, if we just do a uniform triangulation on this final result, then you will see that there are more triangles in the nose region. And from that, after you apply the inverse mapping, you will be getting denser triangulation here. So that's a very flexible effect that we can achieve using the density equalizing map for surface remeshing. And then another application is texture mapping, which is also one application that we just mentioned at the very beginning. So for texture mapping, we can first start with a 3D surface, and then we can map it to a planar domain, and then we can design different texture on that, and then we can use the inverse mapping to map the texture back to the surface. So here's one example. Here are some more examples showing that we can use this kind of approach to achieve different clothes design or different kind of design of plates and so on of different structures. So these are some possible applications of the surface density equalizing map. And then in another work, we also try to use this kind of idea of surface density equalizing map to achieve a medical shape analysis. So in medical shape analysis, here we focus on one problem called the carotid artery flattening problem. So carotid artery is one artery in the human neck, and it's actually highly related to the formation of a stroke, which is kind of which can be very serious. So for stroke, one key criteria is that we want to monitor the plaque thickness here. So if the plaque thickness is too high, then there may be reduced blood flow, and there may be some clots forming here, and that will cause the stroke. So the medical researchers have been finding ways to kind of monitor this kind of formation of or this kind of change in the vessel wall plus plaque thickness. But then if we just directly look into the 3D scans, 3D structures, then that may be very difficult for us to kind of really analyze and study them. So so the medical researchers would like to have one method that flattens this kind of blood vessels onto a planar domain, and then do the comparison and analysis on the planar domain. So in this case, we try to apply our density equalizing mapping technique to achieve that. So as we can see here, we can just flatten it onto an L-shaped domain like this, and then different parts will be with the different thickness easily shown, and then that actually facilitates the systematic comparison of different blood vessels of the same patients at different time points, or of different patients, and that gives us a good way to do systematic comparison between them. So that's one application of the surface density equalizing map. And then in another recent work, we also try to extend that to volumetric density equalizing map. So the idea is that as we can see, actually all the formations, all the problem formations are just based on density diffusion. So we can actually also naturally extend that to 3D. So in this case, we are having a 3D volumetric domain, and then we want to achieve different kind of volumetric deformation effect. And again, we can have a no flux boundary constraint that gives us just the shape being unchanged, but then different parts will be inside the shape will be able to be deformed. Or we can also have a free boundary mapping, and in that case, the overall shape can change in shape. And then the formulation will be just very similar to the 2D case. And in this case, we will just have another discretization of the diffusion equation, and also for the velocity field. And then we can obtain these kind of volumetric density equalizing maps. And one immediate application is that we can achieve shape deformations very easily. So if we have a 3D shapes, we can just construct a volumetric domain to contain this shape, and then we can just run this kind of volumetric density equalizing map. And from that, we can easily achieve different deformation effects. We can set the head to be with a larger density, and that would cause the head to enlarge or expand. Or if we want to achieve some more complicated effects, we can also just set different density at different parts. And the good thing about this density equalizing mapping approach is that it's a continuous process. So if you just take the intermediate time points, you can also see the change continuously, and that actually gives us a way to achieve these kind of animations or continuous deformation effects. So that's also one thing about one good thing about the density equalizing mapping approach. So far I have talked about different density equalizing mapping approach for the planar domain, for surface mappings, and also for the volumetric case. And then in the next work, we then try to find some way to improve the density equalizing map. So we find that actually, although we can see that in the density equalizing map, we can already achieve many different effects and handle many different surfaces, there are still some drawbacks in the kind of previous density equalizing mapping approach. So one drawback is that we don't have any control of the bijectivity. So by bijectivity, we means that basically there is no control in terms of the prevention of mesh fold overs. So in some cases, if you set the step size to be too large, then in some cases, or if the density is too extreme, then in some cases the mesh may have some kind of fold overs. It may actually overlap with another triangle elements, and that would actually cause some subsequent computational issues. And in that case, you may have to kind of reduce the step size and so on. So we want to have a more systematic way to address that. And then there is also no control of the conformal distortion. So at the very beginning, we talk about that there are different kind of major methods for surface mappings. So one is conformal mapping, one is area preserving mapping. And as we can see, the density-equalizing map is actually quite useful for achieving area-preserving mappings or like some kind of like area-based deformations. But there is still no control of the conformal distortion, and we also want to handle that. And then another thing that we want to handle is the presence of landmark constraints. So in some cases, we will have some kind of like landmarks that we want to mesh, for example, like human eyes and nose and so on. So we want to be able to accommodate that as an improvement. And then finally, another improvement is that we may want to also handle multiply connected surfaces. So far, we are just considering some kind of like simply connected surface without any interior holes and so on. But what if we have some kind of like interior holes? How can we extend our approach to handle that? So in this recent work, we try to extend this approach from just solving the diffusion equation to solving a variation model. So this is kind of like the original density equation, I mean the diffusion equation, and then this will be corresponding to that. And in this variational approach, we can also add some other like extra terms in order to further address these issues of bijectivity or conformal distortions and so on. So they are the quasi-conformal terms, and I will talk about that like in the next slide. And then mu is something called the Beltrami coefficients, which I will also talk about in the next slide. And but overall, the good thing is that with this kind of consideration of the variation approach, we will be able to achieve bijectivity, and we will be able to control the conformal distortions and the landmark constraints, and also we will be able to handle multiply connected surfaces. So what are the quasi-conformal terms, and what is the Beltrami coefficients? So here is a quick summary of conformal mappings and quasi-conformal mappings. So conformal mappings satisfy the Cauchy-Riemann equation, and basically is in this form. And you can also rewrite it in this form, partial f partial z bar equals 0. And we know that for conformal mapping, they are angle preserving. That means they will preserve like these kind of like right angles. And also, if you consider the deformation as like a circle packing, then you will see that it actually maps small circles to small circles. So quasi-conformal mapping is generalization of conformal maps in the sense that it is not like conformal, but it is satisfying another equation called the Beltrami equation. So the Beltrami equation is like partial f partial z bar equals mu partial f partial z for some complex value function called the Beltrami coefficient with sigma less than 1. So the good thing about this quasi-conformal map is that it is more flexible than conformal mapping in the sense that we can allow certain level of conformal distortion. And if you consider an intuitive understanding, then like under quasi-conformal mapping, small circles will be mapped to small ellipses with bounded eccentricity. And the aspect ratio change of this circle to ellipse can actually tell us how large the angle distortion or how large the conformal distortion is. So in particular, basically the maximum magnification, the maximum strain gauge, and the aspect ratios, they can all be given by the Beltrami coefficients, mu. So basically it means that the Beltrami coefficient is actually one complex value function that can help us understand, or that can help us like represent the quasi-conformality of a mapping. And that's why we are putting this Beltrami coefficient as one of the quasi-conformal terms in the variational model. And then we also put the gradient of that as kind of like smoothness term. So here's another slides about quasi-conformal mapping. So we know that from the mapping we can get the Beltrami coefficients, and then we can use the Beltrami coefficients to kind of understand how large the deformation is or how large the distortion is. And there is actually also a correspondence between the quasi-conformal mappings and the Beltrami coefficients. And in particular, we can actually like see that like if we are given a quasi-conformal mapping, we can of course easily compute the Beltrami coefficients. Well, if we are given the Beltrami coefficients, we can actually also solve a simple linear system in order to get back and associate quasi-conformal mapping. So in the discrete case, it will just be like that we are solving a sparse linear system, which is a generalization of the Laplace equation. So so it's actually like very efficient to solve, and that gives us a very like effective way to control the distortions by looking into the Beltrami coefficients and then doing some kind of like adjustment or manipulations in the Beltrami coefficients, and then we're constructing an admissible mappings based on this kind of like linear system approach. And by controlling the Beltrami coefficients, we can control the quasi-conformality, and that gives us an effective way to handle both the density equalization and also the quasi-conformal distortions. So here is the overall framework of our density equalizing quasi-conformal mapping, the DEQ mapping. So suppose we are given a surface like this, and in this case, we can directly start with a multi-connected surface with some interior holes. But of course, the method will also work for the case of simply connected surface. So for the initial map, we will just map it to like a planar domain using a conformal mapping, and then we will be solving something like iterative process, just like what we did in the density equalizing mapping work. But in this case, we are considering this variational formulation. And as we just mentioned previously, we have a density term, we have some quasi-conformal terms, and these terms will be kind of like, this will be helping us to control the density equalization or area preserving effects. And these terms will be helping us to control the bijectivity, the quasi-conformal distortions, and so on. And then finally, they will give us like a mapping like this, which is kind of like giving us a balance between these kind of like area preservations or like quasi-conformalities and so on. And so in this process, from the initial map to the final mapping, we will be doing an iterative scheme. So the iterative scheme will be decomposed into two major steps. So the first major step will be something called a geometry modification. So for the geometry modifications, we are just trying to handle the boundary. So this time we will have the outer boundary and we also have the inner boundary. And we want both of them to be kind of like enforced to be circles. But for example, for the interior circle, we can allow it to move. We can allow it to enlarge or shrink based on the density flow, based on the density. So for example, if we have higher density on the left, lower density on the right, then like if we solve the diffusion equations, then naturally the hole should be like kind of pushed to the right. So we want to be able to accommodate that, and that's why we have this kind of geometry modification step. And the thing is that when we move the hole, we can also allow the hole to kind of like rotate. We can allow it to enlarge or shrink, and we can allow it to move. So there are different flexibilities in terms of the motion of the holes. And once we have set up the holes, then we can then use something called the Beltrami density equalizing descent, which is kind of a way for us to do a descent combining both density equalization and quasi-conformal and the quasi-conformal terms. And then we will be like doing an iterative scheme until we get the final mapping results. So for the geometry modifications, the key is that we, as I just mentioned, we can allow the center, we can allow the hole to move. That means we can allow the center to change. And we can also allow it to enlarge or shrink. That means we also let the radii to change. And finally, we can allow the hole to rotate. And that means we can have a rotation factor. So these will be the factors that we consider in the geometry modification step. And then for the BDED, the Beltrami density equalizing descent, we will be basically decomposing these into the three terms. For each term, we can actually get the Beltrami coefficients. We can actually get the descent direction of the Beltrami coefficients. And then by combining these descent direction, we can get an overall descent direction. And that gives us the correct direction to move in terms of the Beltrami coefficients. And as we just mentioned, the Beltrami coefficients is actually associated with the quasi-conformal mapping. So we can, once we have updated the Beltrami coefficients, we can also use that to update the overall mapping. And that gives us the entire like mapping, also like all the vertex positions and so on. And then we can repeat the steps and then do the steps again and again until we get the final result. So here are some results of the DEQ mapping. So for the planar case, we can see that if we set different density at different paths, then we can kind of like push the hole to like here, or if we have two holes, then we can also like achieve the deformations with holes, and also all the interior parts are being accommodated. And here is the surface density equalizing quasi-conformal parameterization. So we have a surface, we can like find some way to map it to a planar domain with different parts being enlarged or strained, and then we can still keep the holes to be circular. And here's a quick comparison between DEM and DEQ. So density equalizing map is that we don't have any guarantee of the bijectivity. So for example, here we can see that there will be some kind of like triangle mesh foldovers. And then the final quasi-conformal distortion can also be quite large in the sense that the norm of the Beltrami coefficient is like quite spread from 0 to 1. And then DEQ is the density equalizing quasi-conformal mappings. So the first thing is that we can make sure that there is no like triangle foldovers in the mapping result. And then another thing is that we can, so here we can see that the final density will be like more or less the same, but then the conformal distortion will be smaller, so they are closer to 0. And recall that if mu is 0, then that means the Beltrami equation is just the Cauchy-Riemann equation. And that means if mu is 0, then the mapping itself is a conformal mapping. So we can see that if we consider element-wise, then the Beltrami coefficient is actually quite closer to 0 when compared to the DEM. And that means for the DEQ, it actually gives us improvement in terms of both the bijectivity and also the conformal distortion. And as we mentioned in the very beginning, we also want to accommodate landmark constraints. So here we can see that we can actually just add some additional constraint in this variation of formulation easily. And so here P is the landmarks and Q are the target positions. And we can easily achieve this kind of land mapping effects. And the iterative scheme is actually quite similar to the DEQ method. And here's just one other example showing that we can have this kind of landmark aligned parameterization. So after talking about these kind of simply connected and also multiply connected open surfaces, then we would also like to extend our work to other surface topologies. So one natural next step will be the spherical topology. That means genus zero closed surfaces. So for genus zero closed surface, as we mentioned at the very beginning, we would basically like to map it to a unit sphere. So in this case, we want to map it to a unit sphere, and then we want to achieve density equalization. And that means we want different parts of the sphere to be expanding or shrinking according to our desired effect. So that basically gives us the motivation of considering this kind of spherical density equalizing map, SDEM. So for this SDEM, we want to achieve spherical parameterization with area preservations or controllable area change. And the pipeline is actually quite similar to the previous one. So this time we have a genus zero closed surface. And then we start with an initial conformal parameterization, and then we would be running some iterative schemes until we can get the final SDEM result. And the idea is that this time we are directly solving the density diffusion equation on the sphere. So we have to develop an iterative scheme to kind of allow the points to move on the sphere and then expand or shrink different regions. And throughout the process, they should all stay on the spherical surface without going outside or inside. So the formulation is actually quite similar as the previous one. So we first discretize the Laplacian, and then we solve the diffusion equation, and we obtain the velocity field. So this time, one key thing is that we have to do a projection, of course, in order to prevent the points from going outside. We want to make sure that after we compute the density field, after we compute the velocity field, we allow the point to move. They will be still moving on the sphere only. So we want to have this kind of projection step. And then once we update the vertex position, one other key issue is that because of this projection step, there is actually some discrepancy between the density diffusion and the actual vertex deformation. So we will be adding one extra step called the recoupling step that recouples the deformation and density. So in this case, what we did is that in each iteration, towards the end of the iteration, we will be redefining the density as the population divided by the current area of the triangle. So that means we are just using the information of the density to be doing one step of descent, and then we will be kind of updating all these things, and then we will be recomputing a new density. So this will be something different from the previous approach. Another thing that is different from the previous approach is that we will be also adding some kind of overlap correction scheme. As we mentioned previously, in the traditional DEM approach, there is no guarantee of the overlap. So, and then in the DEQ approach, there is actually some way for us to prevent overlaps by using quasi-conformal mapping. So here we try to use a similar idea, but we note that the quasi-conformal mapping computations can only be done on the plane. So what we did is that we apply a north-pole stereographic projection to map the sphere onto the plane first, and then we try to do some manipulations to the Beltrami coefficients to make sure that the reconstruct quasi-conformal mapping will be a bijective mapping. And then we can just use the inverse north pole stereographic projection to map it back to the sphere. And then we can do the same thing for the south pole stereographic projection in order to accommodate both poles to avoid missing any paths or any different any regions. And then here is a quick comparison between the result with or without the overlap correction scheme. So we can see that if we have the overlap correction schemes and the ears and also these kind of information, all of them will be without any overlaps. But then if we don't do the overlap correction scheme and then we use the same step size as the previous one, then there will be some kind of mesh fold overs that will be occurring throughout the process. So that means it's actually important for us to add this kind of like overlap correction step. And here are some results for the SDEM. So we can have like some parts being enlarged or some parts being enlarged or strained like together. And then this is the initial density, and this is the final density. We can see that the final density is kind of highly concentrated at one like a peak. So that means the density is highly equalized. And as we also talked about previously, we want to achieve area-preserving mappings. So these are some examples of area-preserving parameterization via SDEM. So again, this is the initial input surface, initial parameterization. And for the initial parameterization, we can compute the area distortions, from which we can see that the area distortion is actually quite spread. That means, the area distortion histogram is quite spread. That means the area is not preserved in this initial mapping. And then in the final mapping results, we can see that the histogram is highly concentrated at 0. That means this is highly area preserving. And we can also see from the visualization that like some parts like these kind of like spikes will be like kind of like restored from these kind of like highly squeezed regions to a more natural region. And same for these kind of like folds on the brain surface, they will become restored and enlarged back. So that's the good thing about this kind of area preserving parameterization. And then we can also use this kind of approach to do surface remeshing for genus zero closed surface. And here is one surface, and then if we want to use the SDEM to do remeshing, then we will be able to achieve a pretty uniform mesh density. While if we are using just the conformal mapping, then we will be getting something like this, in which some parts will be larger, some parts will be smaller. And that's because of the feature that conformal mappings are not area preserving. And here are just another set of examples showing that for the same surface, we can achieve different kind of like remeshing results by just mapping this onto the sphere using our approach, and then doing some kind of like remeshing on the sphere using different number of mesh elements. And at the very beginning, when we talk about the density-equalizing mapping, so the origin is about diffusion-based cartogram, about like showing some kind of like information on the geographical map. And it turns out that we can also apply our spherical density-equalizing map to this kind of like spherical data visualization problem. So we are given a spherical model representing the Earth, and then we can set different density at different regions based on different criteria, and then we can deform that, and this will give us the distorted the cartogram showing these kind of effects. So essentially, we can by our method we can extend the data visualization application to the case of spherical visualization, and that would be very helpful for kind of like further reducing the distortions caused by the usual projections in usual geographical maps. And then we can also accommodate landmark constraints as the previous case. So we can add landmark constraints in solving these kind of combined problems. We can then combine different directions, and then in the iterative schemes, we'll be accommodating all these different harmonic energy or landmark mismatch energy and so on, in order to achieve this kind of landmark aligned spherical density equalizing map. And so in some cases, so of course, in most of the cases, we may just think of mapping a genus zero closed surface to a sphere. But in some cases, for example, if we are handling some kind of highly elongated medical structure called the hippocampus structure, then it may not be the most natural choice for us to use the sphere. So in this case of this kind of highly elongated structure, we may want to use an ellipsoid rather than a sphere. So here in this work, we try to develop an ellipsoidal density equalizing map approach, EDEM approach. So the idea is quite similar, but then in this time we want to be able to change the ellipsoidal shape freely. So we can set the ellipsoidal shape by ourselves by setting this different kind of elliptic radii A, B, C, and then for different ellipsoidal shape we can compute these kind of mappings very easily, and that also gives us flexibility to handle the same surface by using different kind of ellipsoids. You can use a more spherical one, you can use a more elongated one. And then one natural question would be how can we determine the most natural ellipsoid to use? And it turns out that we can also further optimize the ellipsoidal shape by just considering combined energy that combines the density equalization and quasi-conformality. So by considering this kind of combined approach, we can like optimize ABC throughout the iterative process. So basically throughout the iterations, you will be also adjusting ABC to reduce the density error and also the quasi-conformal error. And the effect is that even if we start with just a sphere and we define some kind of density on that, then the final result will be naturally kind of like a naturally stretched a sphere to an ellipsoid based on the prescribed density. Or like if we just start with a sphere as the initial like shape for this lion fast surface, then eventually it will be like kind of like just evolving to the final shape being more stretched ellipsoid. And that gives us the kind of like a way to basically optimize the shape itself so that we don't have to like further define that by ourselves. And then for the ellipsoidal, for the EDEM approach, we can also use that for surface remeshing. So by comparing these different like approaches, basically SCM is the spherical conformal mapping, SDEM is the density-equalizing mapping, spherical density-equalizing mapping, ECM is the ellipsoidal conformal mapping, EDEM is the ellipsoidal density-equalizing mapping. So we can see that like this EDEM approach is actually giving us the greatest flexibility, so that we can achieve the most uniform and also most like smooth elements in the remeshing results. And then we can also extend it to torus, and the idea is quite similar. So we are having a toroidal surface. We can cut it and then flatten it onto the plane, and then we can just solve for the density diffusion on the plane with the periodic boundary condition, and then that would give us the final toroidal DEM, the TDEM. And just similar to the previous cases, we can prescribe different kind of like density distributions and achieve different effects. And just similar to the previous case, we can also handle arbitrary radii. So even if we have a very stretched torus shape, we can also achieve these kind of like mappings. And then we can also achieve high consistency between results with different cuts. So even if you do the cuttings in different ways, the final results will be highly consistent. And then with this kind of like TDEM approach, we can use that for genus 1 surface factorization. And we can achieve like toroidal area preserving mapping or like genus 1 texture mapping. And these are some examples showing that it's actually giving us a highly area preserving mappings. And then we can also combine overall these kind of like density equalizing mapping approaches with harmonic decompositions to achieve different kind of like shape representations or shape decompositions. So for the simply connected open surface case, we can like use the traditional DEM or the disk density equalizing map to achieve these kind of like these harmonic representations. Or if we want to like further handle some more complicated shapes, we can also use the develop something called the hemispheroidal DEM and also some kind of like hemispheroidal harmonics that help us handle these kind of like more complicated shapes for which it may not be the most suitable for us to handle things on the plane. So in that case, we can actually map it to some kind of like part of a spheroid, and then the geometry of the spheroid can be determined by ourselves. And as we can see here, the decomposition is actually giving us a very good representation. And more recently, we have also been developing some kind of like volumetric quantization for tetrahedral meshes. So in this case, we are combining the 3D density equalizing map with the 3D analog of quasi-conformal mappings. So in this case, we are extending the idea of quasi-conformal mapping to 3D by considering the aspect ratios A, B, C, and then we can have balance distortions and so on. So this is just a very simple framework. So we have the initial mapping given by the boundary mapping and the interior mapping. So the boundary mapping will be based on one of our previous work, which is the SDEM, and then the interior mapping is based on just a simple volumetric harmonic map. And then the iterative process will be involving different parts. Of course, this time we have to handle the boundary, we have to handle the interior points, and so on. So that will be a little bit more like computational expensive. But the results seem to be like also very nice in the sense that we can achieve different deformations and so on. And very recently, we have also been trying to use some kind of learning-based method to handle this kind of density equalization problems. And so far, we have obtained pretty good results for both 2D mappings and also 3D shape deformations. And if you are interested in our work, so basically it's just a quick summary about density-equalizing maps, so we can achieve shape deformations for like different domains, starting with the planar domain to surface domain, multi-connected, simple connected, genus 0, genus 1, and so on. And then we can achieve different like area change effects, area preserving mapping effects, and so on. And as we can see, like there are many different applications that we can achieve. And if you are interested in our work, we have upload many of our codes online. So starting from the older like spherical, starting from the older like DEM or volumetric DEM code to the newer like SDEM or like ellipsoidal mappings and so on. So if you're interested, please feel free to try them. So finally, I would like to thank my collaborators, Chris Rycroft, Ronald Lui, Mamo Schaffer, and also my postdoc, Jian Lu, and my students, Shenyu Yao, and us of students like Yang Wen Huang. So that's all for my work. So thank you very much.
Does anybody have a question?
So I'm curious, what is the computational complexity scaling as you increase the dimension? And the application that I'm thinking of is actually improving integration methods in modest dimensions. So there are existing mesh decompositions that work well through d equals 4 or maybe d equals 5. And obviously, when you go to very large dimensions, then you'd be doing Monte Carlo. But the question is, can you push this to 5, 6, 7 dimensions?
So thanks a lot for the questions. So for the first question about the like complexity, so in many of these like approaches, the key is basically just to solve the so let me just go back to. The key would be just to solve the diffusion equation like iteratively. So basically, it would just involve an n by n system where sparse linear system where the n is the number of vertices. So if you have like n being larger, then basically the major complexity will be like just caused by the solving the diffusion equation here, which is a sparse linear system. So we are still pretty manageable. But so far we have just been considering like in terms of the dimensions, we are just considering like up to like 3 dimensions. And of course, the formulation itself should be naturally applicable to like higher dimensions. So, for example, here you can see that like basically we can also like further extend it to 4 or 5 dimensions. But we haven't tried that yet. So that's thanks a lot for that.
Any question else? Oh, I have a question. Can this method, density equalizing map method, be used to like 3D medical diagonalization, like highlight the abnormal organ or something else, or CT or something?
Yeah, that's definitely possible. So so basically, it will be very similar to like this work here. So in this work, of course, we are just handling surfaces, but we can see that we can already kind of like map a complicated surface or complicated structure to a simple shape, and then we can do the comparison there. So for the volumetric case, for the 3D like medical images, then we will be using these kind of like volumetric approaches, and then we can also like computer mapping of different kind of like images to the same domain, or we can compute like a deformation from one shape to another shape at different time points, and then we can use the deformations to capture the shape anomaly. So that's definitely possible.
Thank you. If no questions, please thank the speaker again.
Thank you.